So I want to introduce you to our next speaker, Phil Swan. Phil is the lead principal engineer at the Atlantis project. If you don't know what that is, I encourage you, you're going to learn about it today, I encourage you to look it up online. Phil has a track record of developing successful innovations while working on advanced multidisciplinary projects, including Starlink, HoloLens, and Xbox. He has been granted 38 US patents, including most recently a patent for the Tethered Ring, for which you're going to learn more right now. He is the recipient of 3 corporate recognition awards, and we're very happy to have him here today. Welcome, Philip.
Thank you. Today, at the end of this presentation, you will learn how to go from Earth to space by way of a ring. But I also hope to inspire you to challenge conventional wisdom in your own industries, challenge entrenched thinkings about how things are done. And this is something that we're doing, and I hope you'll look at it and say, yeah, we could do that too. Now, I'm going to jump around a little bit today between technology and business to keep the presentation interesting. I'll be wrapping up by talking about some incremental steps about how we can go from where we are today to a future where we have space infrastructure. The first business is sustainable space launch. So we have some good data already on how much it costs to go to space, and this is some of that data. $5,500 US dollars per kilogram. This is data from 2022. It also costs about $55 million per person to send something to the ISS, $1 billion per ton to send something to Mars. Now, we're doing this today with rockets, and rockets are a very well-established and mature technology, but there are still some innovations in the pipe. For example, Starship, SpaceX's Starship. Now, you can list all the different innovations that Starship is working on, and I've done this in the table. Now, since we don't have any hard cost data for something like Starship, what we can do is look at each innovation individually and ask to what degree we feel it's transformative, and then adjust the price per kilogram to space based on those assessments. But I would argue that we need something truly transformative to make a real dent in the cost of going to space and the environmental impact. And that truly transformative idea is electromagnetic space launch. So the idea here is that with a linear motor placed inside an evacuated tube, you can accelerate a spacecraft up to orbital speeds. Now, the problem with doing that on the surface of the Earth is that when the vehicle exits your tube at orbital speeds, it will simply burn up in the atmosphere like a meteorite in reverse. But if you can place that tube at the edge of space in the stratosphere, then this idea becomes technically feasible. By the way, the cost of doing this drops to $2 per kilogram rather than $5,500. Now, the usual argument against building any kind of expensive infrastructure is that there's not enough demand to justify it. So you look at this curve, which is an example of how people would make this argument. They would say that it would take, say, $110 billion to build this electromagnetic launcher before you get anything off the ground. Whereas if you use a program like Commercial Crew to make rockets more cheaply with the commercial industry, it costs about $8 billion, and then you're starting to get things fly off the ground. Now, this is great for small amounts of small markets, but if you look at humanity's aspirations to, for example, set up a self-sustaining city on Mars one day, that's going to take 1 million tons sent to Mars. So we need to walk our way up this blue curve until we get to the point where we've got 1 million tons on the y-axis here, and then look across to see what the cost is. The cost is $19 trillion. Despite the high upfront cost of infrastructure, the infrastructure approach is far, far cheaper. In fact, you'd be saving something like $19 trillion if you built a tethered ring and put an electromagnetic launch system on it. Now, you may be asking at this point, what is this tethered ring thing that will save me $19 trillion? That would be nice to know that. So we'll move on to technology. Well, tethered ring is a patented technology. It's a dynamic structure. It's a multi-use platform, and it's something that's constructed on the Earth and then winched into space, literally lifted up into space by the action of pulling on cables. The reason I added this 42, anyone want to guess what 42 is about? The reason I added the 42 was to remind me about the question. So the question we wanted to answer with the tethered ring is, using only technology and materials that are available to us today, what is the most cost-effective way to get into space? So the answer to that, we feel, is a tethered ring. But what was very interesting about coming up with an answer is that then we had to re-examine the question and to see what kinds of questions that answer would provide an answer to. And some of those answers turned to relate to sustainability and transition to a carbon neutral economy. So I mentioned it was a patented technology. What this means is the US Patent Office assigned some subject matter experts to study the invention, and they concluded that it was new and non-obvious and that has utility. But I wanted to talk or help you visualize this idea of a tethered ring. So for a moment, just imagine you have a globe, and you turn the globe so that the Pacific Ocean is at the top. And then take a steel ring and place it on the globe, like I'm showing here. And then attach tethers, or let's imagine these being pieces of thread between the steel ring and points above the steel ring on the surface of the globe. Now you could imagine that if you could tighten up each of those tethers, like tightening up the spokes on a bicycle wheel, you could lift the steel ring off the surface of the globe, by a few millimeters perhaps. But this won't work on the scale of the real Earth. So what would happen is that steel ring would collapse like a rubber band at the scale of the Earth. So to prevent that, what we have to do is replace the steel ring with a pipeline. And on the inside of the pipeline, you have to put a maglev track, and they have to support another ring. And that internal ring has to rotate. Now, the rotating internal ring will generate outwards inertial forces. And those are represented here by these red arrows. So these inertial forces prevent the ring from collapsing when you pull it up with the tethers. So essentially what's happening here is the inertial forces are balanced against the tensile forces of those tethers to offset the forces of gravity, which are shown by these green arrows. The tethers should be forked so that they distribute their tensile force around the ring evenly, and they would tend to sag under the weight of gravity. And the steel ring doesn't have to be as thick as we've shown it here. It can be much thinner, and it doesn't have to be as high off the ground. So it's actually quite close to the Earth. It's about an altitude of 32 kilometers where it would be useful. So this is kind of what it would look like on the globe. Finally, you can build it in the Pacific Ocean, but then you can move it to a place where it would be more useful, so you don't have to leave it there. The example I'm showing here is we build it in the Pacific and we move it up northwest in order to place it over New Zealand, Australia, Western Asia, or Eastern Asia, and Western United States, Canada, Alaska. This is what a tethered ring would look like from space if you could put lights on it so you could see it. Without lights, you wouldn't be able to see it. This is a close-up of the tethers to show how they fork. And this is a rendering of the tethered ring in Google Earth, so you can get some landscape. And last thing, I wanted to kind of give you a sense of where the tethered ring size or circumference fits amongst other projects that humanity has undertaken. So right below it is the Great Wall of China, and right above it is the US interstate system. So it may seem huge, but in reality it's kind of in there with lots of other things we've done. Okay, transitioning from technology back to business models. My key challenge with any infrastructure project like this is you need to come up or make the case that it will generate enough revenue or enough value to offset the service the debt that is incurred to build it. And to that end, we've been working on a variety of business models, and I'm going to show you 3 of the interesting ones today. The first relates to something we were talking about earlier today, carbon neutral international travel. Today, this is a business that's serviced primarily by subsonic aircraft. Now, these aircraft are hard to make carbon neutral. For example, lithium-ion batteries are not energy dense enough to electrify these kinds of vehicles. So that's not really a great solution so far. Another possibility is high-speed electrified trains. But the problem with trains is their corridors are expensive. So these corridors fall into 3 categories. There's on-grade corridors, there's below-grade corridors, and then there's above-grade corridors. In each case, there's reasons why these corridors tend to be expensive in practice. And this is a table that shows lots of different corridor types and the prices. And you can see they're all kind of clouded up here on this graph. What we've been investigating is the technical and economic feasibility of a ring-mounted evacuated tube transit system. So a ring transit system has several advantages over airplanes. Like the individual vehicles are small, like business jets, and they depart frequently and they're very fast, and they're autonomous. They travel on maglev tracks, and they don't have like heavy components like wings and engines, fuel tanks, and landing gear. And they can't be hijacked. So the security for riding one of these will be more like a train station or subway security than airport security. In terms of the time it takes to go from place to place, this is an example. These are waterfall graphs showing the travel time from Los Angeles to Kyoto, Japan as an example. It takes about 1/3 the time with the ring transit system versus planes. And geopolitically speaking, international transit projects are actually not without precedent. So the prestigious Chinese Academy of Engineering has already proposed a $200 billion plan to link China, Russia, Canada, and the US by transit system. This is a table of all these different sort of metrics of transit systems. The ones I wanted to bring your attention to, though, are that The cost of airlines is, a lot of it's in the airport, the land for the airport. And the cost of transit systems like rail systems is in the corridors. But with the ring transit system, you really only need little elevator terminuses at the bottom of the elevator cables. And you don't need to have airports, you don't need to have train lines on the ground. So this ends up being a lot cheaper in practice than other systems. But there's other advantages as well. All right, next I want to move on to a kind of an interesting business model that people might not really realize is a potential option. But that is about solar power, generation, storage, and transmission. So the idea here is simply to mount solar panels up on the tethered ring. Now, why would you want to do this? Well, the reason is they'd be more efficient up there. They're above the clouds. They're above 99% of the atmosphere. They don't accumulate dirt up there. They get full power from sunrise to sunset because they're so high up. They can see right to the horizon. They don't get blocked by mountains. And also because the ambient temperature up at the ring is about minus 40 degrees, the solar panels are actually far more efficient and they last longer because of the cool air. But whenever you have renewable energy, you're also dealing with intermittency issues. And so you need storage to reconcile the supply and the demand in the energy generation equation. Now what's interesting about a tethered ring is that that moving ring that I mentioned earlier, it stores a lot of kinetic energy. In fact, it stores about 58 terawatt hours of kinetic energy. And you can add power to the ring by speeding up a little bit, and you can take power out, and you can put power in one place and take it out in another. If you take just half of 1% of that energy and use it for time-shifting renewable energy, that's worth a lot of money. In fact, the amount of storage value in that amount of little shifted energy is equivalent to about $635 billion worth of lithium-ion batteries, and that's not including the recycling costs. That alone would really fund the tethered ring more than like 10 times over. The next model is real estate and tourism. The idea here is to install perhaps about habitable floor space for perhaps about 250,000 people up on the ring. Now that sounds like a lot of people, but think about airplanes. They support 750,000 people up in the air at any given time, so 3 times as many people. The advantage of creating real estate up on a ring is that it's very high quality premium real estate, and you can actually sell it before it's built. You can sell pre-construction real estate. Lots of other interesting projects have done this. So it's a source of early funding. But increasing space tourism in this particular way supports the environment through something called the overview effect. So it has the potential to benefit this environment by convincing millions of people to make lifestyle changes once they've gone up there and looked down upon the earth, or perhaps just vote for the best leaders to prevent global warming. All right, now I'm going to switch it back and talk about technology once again. There's 2 things I wanted to talk about: heritage technologies, which are basically technologies that sort of supply technology to the tethered ring, and capital cost. Let's start with heritage technologies. The first of these is magnetic bearings. Now, magnetic bearings are used in lots of industrial applications because they last longer and end up costing less than traditional mechanical bearings. This video shows a shaft that's being supported by magnetic bearings being hit by a hammer. And you can see the computer system, it quickly adjusts the magnetic fields to keep that shaft from flowing off center. This is very much like the system would support the spinning ring inside a tethered ring. Another heritage technology is carbon fiber. The tethers in the tethered ring are made of carbon fiber. Now, carbon fiber is not graphene and it's not carbon nanotubes. It's an industrially produced material today. The cost is coming down rapidly and the manufacturing capacity is going up exponentially. And there's like a figure of merit for this tethered ring. And that's the cost per kilogram that it supports. So you can make any size or any mass tethered ring you want, but it really comes down to this metric. This graph shows what that metric is. Basically, our reference design is the 32-kilometer high tethered ring. So at 32 kilometers, the cost per kilogram supported would be about $110 per kilogram. Now, to put that in perspective, an A380 has a cost per kilogram supported of about $3,000, and it only supports things at 10.6 kilometers. So this dot is about 100 times higher than this point here on the curve. So it's about our tethered ring is about 100 times cheaper than airplanes at supporting things up in the stratosphere. So it's more like a building than a plane. So next, I want to talk about some incremental steps. Some people have said, like, I can believe this is a technically feasible idea. I can believe this is an economically feasible idea, but it seems like a giant leap for mankind to go from where we are now to having built one of these things. It's a huge project, right? So let's talk about that. The first step would simply to build a magnetically levitated ring in a lab and experiment with it, and then you would move on to a larger scale project where you'd actually put a larger ring in a warehouse. It might be a little bit more dangerous. And you'd also start experimenting with manufacturing techniques to see if you could make this ring cheaply. And then you would go to a demonstrator project where you actually connect a magnetically levitated spinning ring to an electric grid to see if you can time shift energy with it. Now, why would you do this? Well, what's really interesting about magnetically levitated spinning rings is the way that the cost of energy storage scales with the diameter of the ring. This graph shows the energy you can store per dollar for a spinning ring, a magnetically levitated spinning ring, versus lithium-ion batteries and two kinds of flywheels, steel flywheels and carbon fiber flywheels. All this is to say that there's a financial incentive here to create ever larger spinning rings because the costs get very good, and they easily beat lithium-ion batteries after a certain scale. And of course, they're easier to recycle than lithium-ion batteries. They last forever as well. There's no reason they decay. So the next step after this will be to build an energy storage minimal viable product, something that you can sell over and over again and make money with. And you might consider building something like this. This is a wave energy generation device. Inside it there is a spinning ring that stores energy, but spinning ring in here is also used to support the power takeoff units, which are these little pistons. So as the water shifts or moves around the outer hull, these pistons are pushed around and they're supported by the inner spinning ring. Now the reason you would do this is that all the mechanical parts of this wave energy generator are on the inside. And so they don't corrode, they're not subject to biofouling or getting entangled with nets and things like that. And this makes the technology last in the ocean for a long time, which is something that all other wave energy technologies struggle with, and one of the reasons why they can't get off the ground. That's why wind and solar are popular, but wave energy is not. The next step after this would be perhaps to partner up with the particle physics community and build an underwater particle collider. And then we would hopefully at this point be able to jump to the first full-scale tethered ring, but this would be an uninhabited version. It would support the solar panel and the storage ideas. It might support cargo space launch. You could put communications gear on it, for example. And after that, you would go to the full-scale habited or inhabited model where you'd support the transit systems, human-rated space launch, and you'd create that habitable floor space where millions of people could go to look down upon the Earth and see the planet from a new perspective. So I hope I was able to convince you, or at least a few of you, that developing space infrastructure will not only help us transition to a carbon neutral economy, but it will also enable human civilization to expand out into the solar system. If any of this resonated with you, I just hope you'll find me afterwards and ask for me for my card, and feel free to hit me up with tough questions. And if you have any doubts, I definitely want to hear them. If you have some specialized knowledge, that'd be great to share too. But yes, just reach out and let me know what you think. Thanks very much. Yeah, you're welcome.
Very nice.